Hi students, welcome to the video lecture 6 of heat exchangers. So in the today's class we will study the effectiveness NTU relation for parallel flow heat exchanger. NTU is nothing but number of transfer units. So in the LMTD method for parallel flow heat exchanger, so already we have derived this equation, log of Th2 minus Tc2 divided by Th1 minus Tc1 is equals to minus U into A, the bracket 1 divided by Mh into Cph plus 1 divided by Mc into Cpc. The same equation I will write here, log of Th2 minus Tc2 divided by Th1 minus Tc1, this will be equals to minus U into A, the bracket 1 divided by mh into Cph, I will replace it by 1 divided by C of H plus 1 divided by C of C, that is capacity rate of hot fluid and capacity rate of cold fluid, where Ch is given by mh into Cph. The same equation I have written here. Now let us assume any one of the fluid as the minimum fluid and the other fluid as the maximum fluid. Here I have assumed CH as the value of CH is less than the value of CC. That means here we have assumed capacity rate of hot fluid as the minimum fluid and whereas capacity rate of cold fluid as the maximum fluid. That means when CH is less than CC, then we will consider CH as C minimum and CC as C maximum. Now the same equation I will write here, log of Th2 minus Tc2 divided by Th1 minus Tc1, this will be equals to minus U into A. Here from this equation I have taken 1 divided by Ch as the common. 1 divided by Ch I have taken common. So I have written here equation minus U into A. The next step of this equation minus U into A. 1 divided by Ch I have taken common. If I will take 1 divided by Ch as common, then in the bracket this will be 1 plus Ch divided by Cc. Then the equation, if I will solve this equation, then my equation will be in this form only. Minus U into A, 1 divided by Ch I have taken common. So in the bracket, if I will take 1 divided by Ch as common, then this will be 1 plus Ch divided by Cc. Equation remains as it is. So already we have assumed 1 Ch as the minimum fluid. So let me substitute here minus U into A divided by into, it is 1 divided by Ch is nothing but 1 divided by C minimum in the bracket 1 plus, so this will be Ch divided by Cc, the same, where Ch is nothing but C minimum and Cc is the C maximum, the same value I have written here, 1 plus C minimum divided by C of maximum. The next step of this equation, I have substituted Ch as C minimum and Cc as C maximum in this equation. Now if I will remove this log term, if I will keep the equation only Th2 minus Tc2 divided by Th1 minus Tc1, then this equation will be exponential to the power of this equation. I have removed the log term here, exponential to the power of this entire equation, that is minus U into A divided by C minimum in the bracket 1 plus C minimum divided by C maximum. Let me call this equation as equation 1. Now we already know the formula. Effectiveness of the heat exchanger is given by the formula Q divided by Q of maximum, where Q of maximum is given, Q divided by Q of maximum, where Q is given by CH into TH1 minus TH2 divided by Q maximum is given by C minimum, C minimum of TH1 minus TC1. Again the same equation, if I am writing it for the cold fluid, where effectiveness of the heat exchanger is given by Q, that is Q value is nothing but Cc into Tc2 minus Tc1 divided by C minimum of Th1 minus Tc1. So already in this equation we have used Ch as the C minimum and Cc as the C maximum. So let us consider this equation only. So from this equation we are going to calculate the value of TH2. So epsilon into C minimum into TH1 minus TC1 cross multiplication is equals to CH into TH1 minus TH2. So by simplifying this equation, I am going to calculate the value of this TH2 value. So already I have done here, CH into minus CH into TH2, it will come here. So I have taken the equation to this side, left side. So this becomes plus CH into TH2 will be equals to CH into TH1 as it is. So minus, I have taken this equation to the right side. So this becomes minus epsilon into C minimum of TH1 minus TC1. So with this equation, I have calculated the value of TH2, where TH2 is equals to TH1 minus epsilon C minimum divided by CH in the bracket TH1 minus TC1. So similarly, by solving this equation, in the same manner how we have calculated TH2, in the same manner I am going to calculate the value of TC2, where TC2 is nothing but temperature of the cold fluid at the exit of the heat exchanger, where TH2 is the temperature of the hot fluid at the exit of the heat exchanger. TC2 is the temperature of the cold fluid at the exit of the heat exchanger. With this equation, solving this equation, similarly this and this cross multiplication, this will be equals to this. So with that equation, I have calculated the value of TC2. Now let us substitute the value of that TH2 and TC2 values in equation 1. That is TH2 minus TC2 divided by TH1 minus TC1. That will be equals to exponential of, I have written here minus NTU, where exponential of minus U into A divided by C of minimum is nothing but NTU. This is replaced where NTU is nothing but U into A divided by C of minimum 1 plus C minimum divided by C maximum is nothing but the capacity ratio. Directly I have written C minimum divided by C maximum as C value. So this is the value of TH2 and this is the value of TC2. That is TH2 minus TC2 divided by TH1 minus TC1. So here is this TH1. If I will solve this equation, TH1 minus TC1. So TH1 minus TC1 I have taken common throughout this equation. So in the bracket, if I simplify this equation, then this will be 1 minus epsilon into C minimum of 1 divided by CH plus 1 divided by CC. So if I will solve this equation, I am going to get this equation only. I am going to get this equation. This is the simplified form of that equation. That means I have taken TH1 minus TC1 as common. So in the bracket, this will be 1 minus epsilon of C minimum in the bracket 1 divided by CH plus 1 divided by CC exponential of minus NTU in the bracket 1 plus C whole divided by this. Sorry, this is not related to this equation, only it is related to this equation. TH1 minus TC1. So this TH1 minus TC1 and this TH1 minus TC1 gets cancels. So my equation will remain 1 minus epsilon of C minimum in the bracket 1 divided by CH plus 1 divided by CC equals to exponential of minus NTU in the bracket 1 plus C. So let me call this equation as equation 2. So here I will take again 1 divided by CH as common. Then equation will be 1 plus CH divided by CC. So 1 minus epsilon. If I will take 1 divided by CH as common, then CH is C minimum. C minimum gets cancels. So my equation remains 1 minus epsilon in the bracket 1 plus C. This will be equals to exponential of minus N in the bracket 1 plus C. So this NTU in the short form, I have written it as N. We can write it. NTU is nothing but N is nothing but NTU. So 1 minus epsilon of 1 plus C is equals to exponential of minus N in the bracket 1 plus C. This C indicates C minimum divided by C maximum. C is nothing but capacity ratio, where C indicates 1, that is C minimum divided by C maximum. So if by solving this equation, 1 minus exponential of minus n in the bracket 1 plus c. This will be equals to, I have taken this term to the right side. So by solving this equation for effectiveness, I am going to get this final expression in this form. It is effectiveness equals to 1 minus exponential of minus n in the bracket 1 plus c bracket complete divided by 1 plus c. So this is the effectiveness for the parallel flow heat exchanger. So now in the previous class, the previous starting, we have assumed CH as the C minimum. Now I will consider CH is greater than CC. Here we will consider CC as the C minimum and CH as the C maximum. So taking the from equation 2, directly from equation 2, let me write this equation: 1 minus epsilon C minimum in the bracket 1 divided by CH plus 1 divided by CC. This will be equals to exponential of minus n bracket 1 plus C. This is from equation 2. So here in this equation, I will take 1 divided by Cc as the common value. 1 divided by Cc as common. If I will take 1 divided by Cc as common, then in here it will be Cc divided by Ch plus 1. Cc divided by Ch is nothing but C minimum divided by C maximum, which is nothing but capacity ratio C. 1 minus epsilon in the bracket C plus 1. This will be equals to exponential of minus n in the bracket 1 plus C. So if I will solve this equation for effectiveness, then I am going to get the same expression how I have got here. That means if I will assume any one of the fluid as the minimum fluid and the other fluid as the maximum fluid, I am in both the conditions I am going to get the same expression. So this is the final expression for the effectiveness NTU method for the parallel flow heat exchanger. Now there are some special cases, some special cases for this effectiveness NTU method for parallel flow heat exchanger. So for if the problem is based on a condenser or a boiler, so usually in the boiler or condenser, one of the fluid undergoes a phase change. Phase change means in the condenser where vapor is converted into liquid, in the boiler where liquid is converted into vapor. That means in such conditions the maximum C maximum will be equals to infinity. This is the standard condition. Then if C maximum is infinity, then this capacity ratio C will be equals to 0. Then effectiveness of the parallel flow heat exchanger, if the problem is based on a condenser or a boiler, then we are going to get the effectiveness of the heat exchanger in this form: 1 minus exponential of minus n. We are substituting the value of C equal to 0 and my final expression is in this form. Now second case, when CH is equals to CC value, it is not greater or it is not lesser. When both the values are equal, that means C minimum will be equals to C maximum. In such condition, we are going to get capacity ratio C is equals to 1. That is, C is nothing but C minimum divided by C maximum. When both the values are equal, CH divided by CC both gets cancels, then this C will be equals to 1. So when we will get this C is equals to 1, it is a typical case of a gas turbine regenerator. If the problem is based on the gas turbine regenerator, in such condition we are going to get the value of C as 1. There the effectiveness of this heat exchanger is given by this formula, where effectiveness is equals to 1 minus exponential of minus 2n divided by 2. I have substituted these values in the standard equation. So all these values we are going to get the values formulas in your data handbook. You go through the data handbook, all these formulas are available in your data handbook. Even though effectiveness, NTU method for parallel flow heat exchanger, LMTD for both parallel flow and heat exchanger, for both parallel flow and counter flow heat exchanger. So all these formulas are available in your data handbook.